let's take a totally different example. This time we are going to go to 4 constraints. Okay, so but again geometry will help us solve this problem. Now note, I'm going to pick a problem whose solution I can infer from geometry, just so that it's easy to verify and understand. Okay, so I'm going to give you an objective function fx. This time it's not going to be simple linear objective. X1 minus 3 by 2 whole squared plus x2 minus 1 by 2 whole squared. Okay, sorry, to the power 4. Okay, otherwise it would have been very simple to sketch. Okay, so this is my objective function subject to four constraints. They look complicated, but actually they're not that complicated. First constraint, what does it look like? 1 is less than x1 plus x2. That means it's a straight line, slope 135 degrees, and I want to be below it, right? So, right. Second constraint, 1 is or x1 minus x2 is greater than 0. Or you want to start with the fourth constraint. What is the fourth constraint saying? x1 plus x2 is greater than minus 1. So it's a line parallel to this guy and I want to be above it, right? So it's giving me this. What about the other guys? So it's actually a diamond. And very quickly you can confirm, supposing I take the origin. The left hand side in all 4 cases will become 1, right? 1 is greater than or equal to 0. So the origin belongs to this feasible set, which is what, I mean, that's just, when you draw a feasible set, it's good to take a few test points to make sure that you didn't flip an inequality and, you know, mess it up that way. Okay. So this is, this point is going to be what? The coordinate points are going to be 1, 1, 1, 1, right? So the 1, 0, 0, comma minus 1, minus 1, comma 0, 0, comma 1. These are the 4 points. All right. Okay. Now comes the part of the objective function. So it's not a quadratic form, that much we can see. 1 is square, 1 is to the power 4. But we can identify the point at which this function goes to 0, which is 3 by 2 comma half, right? So 3 by 2 here and half maybe here, right? So this is the point where this function goes to 0, right? And from here I can draw some, they won't be circles, because it would be circles if it were whole squared instead of power 4. But they will be, you know, contours that will look somewhat like this. We can later draw this on MATLAB or whatever and see. And so you will just have to take my word on this, that the contours will look like this. Okay. And the way these contours work is, you know, they would sort of go like this. So, you know, without having plotted this over here, you know, if I had an actual MATLAB plot, you would see that this the subsequent ones would go inside it. So the contour which touches, the blue contour which touches the red line at the earliest is the guy that's going to be the solution. As the contours grow, the function value is increasing, right? The least value of f is where? At the dot, right? So at the center C over here. As I start increasing, the function values, these contours grow bigger and bigger and bigger, right? So this point at which this guy touches over here is actually the solution to this problem, because if I go any further into the feasible set, the function value is going to increase. Okay, so you have to take my crappy drawing at face value for believing this. Okay, so this happens to be the true solution. Okay, so here is also how the KKT theorem helps us to check our intuition. How will it help us check our intuition? We'll take this point 1, 0 and subject it to KKT. If it works, then it's a solution. Okay. So this is C1, C2, C3 and C4. I should not put equal to, but yeah, equal to is good. All right. Now so the point to test is 1, 0. Okay. Now at 1, 0, which constraints are active? C1, right? You can substitute into this 1 minus 1 equal to 0. First one, C1 is equal to 0. C2, if I substitute 1 minus 1 plus 0 is also equal to 0. C3, if I substitute 1 plus 1 is 2 minus 0, so 2 is greater than 0, so not C3. C4, 1 plus 1, 2 greater than 0, so not this thing, right? So I have two constraints that are active, right? So when I write my Lagrangian multipliers, which guys do I have to set to 0? So this is step 1. Step 2 is Lagrange multipliers. Which one should I set to 0 straight away without doing any calculation? Lambda 3, lambda 4. So let's set those guys to 0 immediately. Lambda 3 equal to 0, lambda 4 equal to 0. Done. I cannot say, can I say something about lambda 1, lambda 2? What? Greater than equal to 0, why? Inequality constraints. Okay. So like this we proceed systematically. Excellent. Next is, let's get this Lagrangian into business. If this guy 1, 0 is the optimal point, what should happen? Grad L should be 0. Grad L should be 0. So let's look at grad L. So here is my, so first of all, what is L over here? F minus lambda 1 C1 minus lambda 2 C2. Do I need to write lambda 3, lambda 4? No, they are 0. So implies that grad F should be equal to lambda 1 grad C1 plus lambda 2 grad C2. So now let's write that down. What is grad F? 2 times x1 minus 3 by 2, that's the first component. Then 4 times x1 minus half, sorry, x2 minus half whole cube. This is my grad F. And what is my grad C1? Minus 1 minus 1. Okay, so lambda 1 minus 1 minus 1. Lambda 2. What is my grad C2? Minus 1 comma 1. Okay. The point is 1 comma 0. So if I substitute 1 comma 0 into this, what will I get? 1 minus 3 by 2 is minus half, multiplied by 2 is minus 1. So this is minus 1. And this guy is 0. So what do we get? Minus half, because it's minus 1/8 into 4, which is minus half. So lambda 1 and lambda 2 have to satisfy this. Okay. Do you, just by looking at it, do you think it's going to be possible? Yes. So what was your intuitive way of arriving at it without solving? That's very important. They are linearly independent, right? I could write this as minus 1, minus 1, minus 1, 1, lambda 1, lambda 2. I could write it like this also. And you can look at this matrix, right? It's not it has it's an invertible matrix, right? The two columns are not linearly dependent, so it should be possible to invert it. However, that's not good enough, right? What do we have to also check? We have to check whether it's positive, I mean non-negative or not. So can you solve this? What do we get? Lambda 1 equal to 3 by 4, that's right, and lambda 2 equal to 1 by 4, which is greater than equal to 0. So our test point 1 comma 0 turns out to be the optimum point. So you don't have to have perfect drawing skills or MATLAB always. Just quickly subject your KKT test and you're done. Okay. Right. So straightforward. Again, just to revise what we did, bring your candidate point, identify which constraints are active. Why do we do that? So that step 2, we can knock off the lambdas which are 0, right? So lambda 2, sorry, lambda 3, lambda 4, 0, we got rid of them. From that we form the Lagrangian. From the Lagrangian, we said grad Lagrangian should be 0, and then we solved for it. Is it possible? Answer is yes. Are those Lagrange multipliers non-negative for inequality constraints? Yes. The point is passes the test. Okay. If I had an equality constraint in here, what is the thing that I have to not worry about? Non-negative need not be the case. Okay. All right. So that's what we are going to do as far as first order necessary conditions for constraint optimization go. Okay. There is a huge amount of problems that you can solve using this alone. Okay. So we won't be going into second order conditions in this course, although you can refer to Nossel's book. I think chapter 12 will give you the Hessian related conditions as well. All right, so this brings this to an end. The next thing that we will start is we'll give you a algorithm to actually solve this problem, which is called the projected gradient descent method. I already gave you an intuitive feel for what projection means. We will formalize that and come up with an algorithm, which will be just as simple for you to code and use in MATLAB as was gradient descent. Okay, so that will be your algorithm that you can use for solving constraint optimization. Okay, so here we have the also known as PGD in short. So everyone knows what the problem is. I have minimize x, f of x, right? X belongs to some feasible set. Okay. As an example of what we will look at, I can have something like this. Right. So if I just did minimize ax minus b whole squared, this could be, for example, a linear least squares problem. Right. Now I can make things a little bit more interesting. I can say something like this. So what is this saying? Minimize this ax minus b whole squared such that the length of the solution is inside the unit ball, right? Here the dimensionality is not specified, so that's why I'm calling it a ball, n-dimensional ball. Now these kind of problems you can imagine if I have constraints on power. My nodes have in a sensor network or an antenna array, they have only maximum unit amplitude that they can put out. This is the kind of problem that I'm interested in. So that's what we're going to try to solve. Okay. So before we get into projected gradient descent, we'll quickly review gradient descent and figure out what other small modifications we need to make in order to make it work for a constraint optimization. So recap of gradient descent. What is the first thing that we did in gradient descent? Pick a random starting point or use some intuition to arrive at a good point, right? So let's just say pick, I won't say random, I'll just say pick a starting point x naught that lives in R. Okay. Next. Yeah, so I mean we need to loop until convergence is satisfied, and then within that we'll calculate a descent direction and step length. I need to know how much to walk, right? And then I will check convergence satisfied or not. Okay. So loop till satisfied. Okay, so I'm writing it like this. Please don't write this way in the exam. Okay, loop till satisfied. So find minus grad f. I need to find. That's the gradient, negative gradient. Okay. Find alpha k. Okay. I've got these, and then I update. Xk plus 1 is equal to xk plus alpha k. Let's write this as minus. That's basically it, right? That was all that gradient descent was. Do this. Okay. Now the PGD, projected gradient descent, is a small modification. I do this step. I continue to do gradient descent the way I have done, except once I get xk plus 1, here is where the problem can happen, right? We can just intuitively think about it. Xk was a point which was feasible, and I'm trying to improve it by going to a better point. So I got my gradient direction, I went in the negative of it, found a step length. What could go wrong? Xk plus 1 could jump out of the feasible set. That's the thing that I have to worry about. So at that point, what I do is I use a projection operation to make sure that I'm still feasible. Okay, so I say xk plus 1 is equal to P defines the projection operation, underscore, or rather the subscript omega says project into this. Okay, and what do I have over here? The same thing, xk minus alpha k grad fk. This is the, in a nutshell, this is what projected gradient descent is. You do vanilla gradient descent, but you do a projection step. So this ensures that xk plus 1 is feasible. Okay, and that's about it. And this surprisingly simple procedure has its own proof of convergence. It works. It actually works. All right. So however, there is a catch. What is the catch? This projection operation, what I showed you a few slides ago, where I draw some object and I just draw a perpendicular on it. I can do all of this drawing perpendiculars until class 12, right? I mean, if I have n dimensional, then what perpendiculars am I drawing, right? So this projection operation is actually a mini optimization problem in itself, right? So let's now write this P operator formally. P, this thing is a projection operation. Operator. So I give it a point x naught. Okay, let's not call it. Okay, x naught is not the starting point. Let's call it x star. Okay, it's an optimization problem. So I should be able to write it as minimize something something, right? So argmin. My variable of optimization, where is it allowed to roam? In the feasible set. So x must belong to this. Okay, what is the objective function that I'm trying to minimize? So you have given me a point x star. Output should be, an x star may be outside. So what am I trying to minimize? The distance between x and x star, right? So common sense says that this should be, I mean, can I put a squared here? Makes no difference. It's the same thing. So usual this thing is this, right? Just a little bit of convention. The literature likes to put a half over here. So this is the projection operation, and this projection operation, input is a point in Rn, output is also a point in Rn. Okay. So the rest of the details of PGD we will discuss subsequently, but this is all that we need to do to get a working constraint optimization algorithm going. Okay, very simple, right? It's simple as long as this sub problem is easy to solve. This may or may not be easy. So we'll explore different types of projection operations in what follows. Okay. Any questions on this? Okay. So I will see you guys tomorrow then. Well, if you write your projection operation in an efficient way, if you give it a feasible point, without doing much calculation, it will give you the same point back, right? What is the projection operation applied to a point within omega? It's the same point. So if you write it carefully, your algorithm should just send you back that point without wasting too much time.